So today I am going to talk about Kramer's Boolean method. It is also known as WKB method, right? So here I will talk about a brief introduction to this method. So this method is useful, is a very useful approximation and it is used for the problems where potential is slowly varying, right? Potential is not constant, but potential is slowly varying. Right, so these are the problem for which this is very suitable. And the another thing with the potential is that the potential remains almost constant. Potential remain almost constant over the region of the order of de Broglie wavelength. So this method is also known as semi-classical approximation. This method is also used to obtain approximate solution for time independent Schrodinger equation. Time independent Schrodinger equation. It is particularly useful in calculating bound state energies, and tunneling rates through potential barriers. So to understand this means to understand this WKB method, let us recall some basics. Right? So for this, consider a particle whose energy is greater than the potential, and we are having a constant potential. So for this, let us draw a diagram. Right, so it is the potential of the particle potential barrier, and it is the energy of the particle where E is greater than this. And let us consider another case. In this case, this is the potential. It's a constant potential, it is also constant, but here the energy of the particle will be this, means it is smaller. It means energy of the particle is small. Energy of the particle is smaller than the potential, right? So there are two different cases. The first case is in which the energy is less than the potential and energy is greater than the potential. These are the two cases which we am considering. Means what we did, we have considered a particle here. We consider a particle of energy E and this particle is moving through a region with potential V. Potential is a function of x, but it is a constant here, right? So V is constant. So this is the case which we are considering here. Now let me try to write down the Schrodinger wave equation for this problem. So Schrodinger wave equation for such a case can be written as, now let me write down the Schrodinger wave equation. So for such a case, this is the Schrodinger wave equation: h cross square upon 2m d square psi over dx square plus v psi is equal to e psi. Here what we have chosen, that v is a constant value. Now we are having two cases. The first case is that when the v is, or energy of the particle is greater than the potential, and another case is energy of the particle is less than this. Let me briefly talk about it. So if we solve Schrodinger wave equation for this, then the wave function which we are getting, it is a exponential of plus minus iota kx which we are getting. And for this case, the wave function comes out to be psi x is equal to a exponential plus minus kappa x. That's what we are getting here. Here the value of k will be equal to 2me minus v under the root upon h cross, and here the value of kappa is equal to 2mb minus e divided by h cross, and it's under the root. Now let us try to see these two wave functions. Here this is a periodic wave function. Psi is periodic and oscillatory. That means its behavior is sinusoidal. And here the psi varies exponentially. This is the basic difference between these two wave functions. And in this case, here the plus sign indicates that particle traveling to right direction, and whereas minus sign indicates that particle travel to the left. So that's what is there. Now consider the first case. where energy of the particle is greater than the potential, and we call it as the classical region. Classical region. So in this case, the wave function is oscillatory. Wave function is oscillatory with fixed wavelength, that is lambda is equal to 2 pi upon k, and fixed amplitude. Fixed amplitude for the case when V is constant. So what in WKB approximation, we assume that Vx is not constant, but it varies slowly. Very slowly in comparison to wavelength. Comparison to lambda. That's what we will assume in the WKB approximation. So that over a region of wavelength, potential is essentially constant. Potential is essentially constant. That's what we will assume. So keeping this in mind, we suppose that psi is practically sinusoidal, but amplitude changes with x. Thus wave function varies sinusoidally. Wave function varies sinusoidally. Thus wave function varies sinusoidally, but its amplitude is a very important point. What its amplitude changes with x. Oh, sorry, I repeated it. Yeah. Thus wave function varies sinusoidally. Let me correct it. We suppose that sinusoidally but amplitude, here it is but amplitude changes with x. So thus wave function, this is very important, but thus wave function varies sinusoidally but in addition to it wave function is modulated by gradual variation in amplitude and wavelength. Let us try to understand this line diagrammatically. So suppose it is the energy and the potential is like this. This is the potential, this is the energy, and V is a function of x, and say it is x-axis, along x-axis, right? And these are the turning points which we have to keep in mind, right? And it's like this, it is x, and say it is the potential, it is a function of x, and it is the energy, it's a constant. Now there are two regions. One region is here energy, here potential is greater than E, and here it is also potential is greater than E, and it is the region here potential is less than E. So this is the first case about which I am talking, and this is also known as classical region. And these are the turning points. Let me change the color of this line. So green colored lines, these corresponding to turning points, means at energy is nearly equal to V. Now what will happen, as I stated here, keeping this sentence in mind, it looks like this. In this region it was like this, amplitude varies like this, it also decreases, wavelength also decreases, sorry, it's like this, and wavelength slightly increases, and so like this, right? That's what will happen in this region, and in the second region it exponentially decreases. So this is basically the WKB approximation. This is a very brief introduction to WKB approximation. So that means what's going on in the second region, means for the second case, where V is greater than E, the wave function not varies sinusoidally but varies exponentially. Right, so this is the modification in this slowly varying when the potential is slowly varying. So this is how the wave function will vary. So this is all about the brief introduction to WKB approximation, and in the next lecture I will talk about it by considering the Schrodinger wave equation, and I will do little algebra, try to appreciate it. Right, so that's all for this lecture.